final thoughts on camber line design. So we've learned that the camber line, the distribution of the camber line, or the strength of the vorticity along the camber line, I should say, is directly related to the delta pressure from the upper and the lower surface, and the strength of gamma depends on the curvature of the camber line, or the slope of the camber line at any location. Okay, so the camber line really is responsible for helping us control the delta P between the top and the bottom. The thickness of the airfoil, on the other hand, is responsible for the average of the pressure between the upper and lower surfaces. So in fact, if we look at these two airfoils, this is remember the orange one is a 2412, and the blue lines here are the uniform load with 12% thickness. These both have the same thickness distribution, and you might notice that if I averaged the upper and lower surfaces of both airfoils, they would actually follow basically the same line. So the average, the average of the orange surface, the upper and lower, is about right there, and the average of the blue upper and lower surface is about in the same location. So the average of the upper and lower surfaces is determined by the thickness distribution of the airfoil, which for these two airfoils is the same. However, the difference between the upper and lower, the difference in pressure between the upper and lower surfaces is determined by the camber line. Okay, so we can link the camber line to the strength of vorticity along that camber line from thin airfoil theory, and back out what the camber line should look like for a given delta between the upper and lower surfaces. But to get the average pressure, we have to have some way of getting thickness distribution. Now, I have a hunch, and I haven't seen this done. Granted, I haven't looked very hard for it, but I have a hunch that you could do something similar to thin airfoil theory, but instead of using, well, let me just write down here. So gamma is related to our delta P, and I think what you could use is if you look at lambda as a strength of a source distribution. So gamma was our vorticity distribution, and I think if you used some analytic solution for sources, the source, you could have a sheet of sources here, or source distribution strength along it, that would basically govern the thickness of an airfoil. And you could do that without any camber to come up with the average pressure that you're looking at for here, and with zero camber. But then and then you'd add the gamma for the delta P that you're looking for up here. Anyway, so that's just a hunch of mine that you could do something similar to thin airfoil theory, but use a source distribution sheet instead to back out for a given average pressure over this airfoil what the thickness should be. Those should be related. So again, I haven't worked through that and I haven't seen it done, but I believe it could be done, and maybe somebody's done it and I'm not aware of it. One other thing I want to point out is that near the trailing edge, for most airfoils, we have a very sharp pressure gradient. This is a very strong adverse pressure gradient. Remember, the pressure here is on the y-axis is flipped, so these points up here are very low pressure, and as the flow moves down the airfoil, it's actually going to a higher pressure. This is called the adverse pressure gradient, and that induces separation. And it's something that the flow doesn't like. So going from a low pressure to a high pressure. Well, once we get here to the trailing edge, then it dramatically increases in pressure back to the stagnation pressure at the trailing edge. So and this is very common for airfoils to do this. One thing that some designers do in order to mitigate that is to actually bring the trailing edge to a cusp. And by by using a cusp at the trailing edge, this adverse pressure gradient is mitigated a little bit, and you might get something, a little bit more benign back here. So that helps with that adverse pressure gradient a bit. But the manufacturing a cusp is extremely difficult. And so that's not something that's commonly done. Usually you just bring your airfoil together at a point. And when you do that, if it has some finite angle there at the trailing edge, then you will get a very strong adverse pressure gradient, which basically induces separation. So a lot of times you'll have some separation here very near the trailing edge. Just because of that really strong adverse pressure gradient, and that increases your drag, which is something that we don't like, but we basically live with it because the cusp is very difficult to manufacture.